Okay, so it's a big pleasure for me to have Rémi Adam here today. So he will be talking, as you can see, on the quest for the diffuse gamma ray emission from galaxy clusters. So before that, let me just say a few words about his trajectory. So Rémi is now at the LLR in Paris, but before that, well, he got the PhD in 2015 in Grenoble. I don't know, whatever.
Grenoble, yes.
Yes. Then he moved as a postdoc to Nice in the south of France. He stayed there for a couple of years, if I remember correctly, and then he moved very briefly to Teruel, to CEFCA, for a few months, because he got then the permanent position at the CNRS in this lab in Paris, LLR, in 2018, more or less.
Yes, I think so.
Yes, okay. And then, well, he's been working there since then. His main expertise is actually something, of course, really, I mean, it's really related to this particular talk. He's an expert on galaxy cluster physics, on cosmic ray astrophysics, and he knows a lot about X-rays. Before that, actually, you were also doing CMB polarization for Planck, I think.
So this was doing my PhD thesis, basically.
Yes, okay. So he also has some expertise on that, as you can see. He has a very broad expertise, I would say. And he was also involved in nuclei. And more recently, since a few years ago, he also got involved in CTA, the Cherenkov Telescope Array consortium. We're also members here, and we are actually now collaborating very closely with Rémi in this kind of galaxy cluster topics. So again, my big pleasure to have you around, Rémi. I hope this is only the first time that you will be coming. Yes, please go ahead.
Okay, so thanks a lot, Miguel, for this very nice introduction. So I don't know how you do usually, but if you want to interrupt me, and if you have any question, it's totally fine for me. And yeah, exactly as Miguel was saying, so I'm going to talk about the galaxy clusters, and in particular, one specific wavelength, which is gamma rays, but we will see that it's also connected to other wavelengths, and we will try to see why. Okay, oops. No. Okay, so this is the outline that I'm going to follow. So first of all, I want to introduce galaxy clusters in general as cosmic laboratories. Then I want to talk, in fact, about two different things. The first one would be the gamma ray emission from the Coma Cluster. So because with Fermi, we will see that there's something maybe interesting to look at. And the second part will be regarding CTA. So as Miguel was saying, we are working together, and in particular, we are working on the preparation of CTA. And so I will tell you a bit more about this one. Okay, so let's start from the beginning, in fact. Oops. No, but wait. Yes, okay. So I like to start, as Miguel was saying, I'm coming from the CMB field, in fact, so I like to start from this picture that you all know, I guess, and I haven't seen picture in the IFT. So this is the universe as it was very short time after the Big Bang. And from this image, you see that the universe is very homogeneous, but you see that there are also some tiny fluctuations. And the question is that, well, when you let evolve this universe, as done, for example, in this simulation, if it's working, yes. So we see that these tiny fluctuations, they collapse under gravity, and they form what we call the large-scale structures. And in particular, at the nodes of this large-scale structure, we will form what we call galaxy clusters. So from a purely cosmological point of view, these galaxy clusters, they are like peaks in the matter density field. But then, I mean, there is also a lot of interesting astrophysics going on. So you see what happens. So for example, you see that during this merging process, you see that there are a lot of shocks, turbulence also happening. Okay, maybe on the simulation we don't see so well, but there are also galaxy formation that will also introduce energy directly in this environment. So you see this nice shock feature. So for example, these two clusters will eventually collide in giant mergers. So all these basically, you see this very nice shock front here. And so all this basically is we take this kinetic energy coming from structure formation, and we will convert it somehow into heat, but also into other kind of energy, as we can see here. Okay, this is more or less what I've been saying. In fact, the structure formation energy, you convert it into heat. So this is most of the energy that end up in heat, around 80%, let's say. But you have also a lot of well, non-thermal processes for example, turbulence. You can see an image of a cluster here where we see these features that are related to turbulence. Also, the presence of magnetic field, cosmic rays, and so on. So an example here of accretion shocks that happen at the boundary of cluster. This picture you will recognize, of course, we will have pictures with IFT. Also, this is the bullet cluster, a major merger. And also, as I was just mentioning briefly before, you have also directly energy injected into the medium from, for example, compact sources like AGN, which produces giant jets, very powerful radio jets that will interact in the surrounding and producing also this, feeding this cosmic ray and non-thermal components. So the big question is how all these components will interplay together, and also even what is the amount of, so I told you the heat is about 80%, but for example, for cosmic rays, we don't really know what it is, the amount of cosmic rays in this intra-cluster medium. And so for us today, we will mostly focus on this part, in fact. But before that, okay, let's start very generically. How can we look at galaxy clusters? So the first obvious thing, even in the world, galaxy clusters are made of galaxies. So the first obvious thing maybe is to look in the optical. So you can see, if you have good eyes, so I don't know, but maybe you can recognize the galaxy cluster. In fact, there are even 4 different subgroups in this cluster. So I don't know if you can do it with your eyes, but basically you can see these 4 subgroups, they are separated here. So by doing this, you will trace the stellar population. Another way to use optical data is to reconstruct the distortion from the cluster mass that is applied to background galaxies. In this case, you can infer the total mass using gravitational lens. So this is what is shown here. You can see these contours, they are mostly showing the mass distribution in this cluster. So here we talk about galaxies, but we can also use other wavelengths, such as the X-ray, for example, in which you can trace the thermal gas, in this case, where you have the brainstorm emission from the thermal gas that is mainly tracing the gas density. So in this image, you see, it does not really resemble to what you were seeing before, but more or less you see the same, yes, this one. More or less you see the same overall shape, let's say, a bit elongated like this. And in this map, you will see the thermal gas density. You can also get temperature with X-ray and also hydrostatic masses that are important, for example, for Judith, for example, when she's studying the dark matter emission from clusters. Another, it's going fast, like this. Another way to study this thermal gas is to use what's called the Sunyaev-Zeldovich effect. Basically, this is the interaction between the CMB photons and the hot electrons in the cluster that are producing this CMB spectral distortion. And like this, you can probe the thermal gas. So you see X-ray and Sunyaev-Zeldovich effect, they are probing the same cluster component, the thermal intracluster medium, but in a very complementary way. So this is generally very useful to use. And finally, if you look in the radio, and also in gamma ray, we'll see gamma rays after. So this is a radio emission. You see that there is also a non-thermal component, and also maybe some dark matter, but I will not talk too much about this. And basically, with radio, you are tracing particle acceleration and magnetic field, because this emission is related to diffuse synchrotron emission, this image. Okay, so here we have reviewed all these different wavelengths that are useful for us. And now let's see if we put everything together, we produce these very beautiful images of galaxy clusters, and even more beautiful, but maybe, well, not as beautiful maybe, but even more data. And what you see is that it's becoming very messy, but on the other hand, you have a huge complementarity between these different wavelengths, and you can really start understanding what is going on and how these clusters are forming. So for us, we will focus on gamma rays and this particle acceleration, but in fact, we need to really model everything. We'll see that we need to account also for the other wavelengths. Okay, but before entering into the details, okay, let's look a bit more at this diffuse radio emission. So maybe you see on this image, in fact, that it's not that simple. There are different components. You can already see, for example, here you can see there is some smooth and a bit faint diffuse emission, which we call a giant radio halo. Okay, we will see what it can be later. You have also on top of that here some like filamentary structure, which we call radio relic, and which are believed to trace a shock directly in the intracluster medium and directly tracing particle acceleration. You can see also that there are some unfolding tail radio galaxies, for example, this one, which might not be related to the cluster, but it might be also. And this one, in fact, is a foreground. So this is basically a radio galaxy emitting like jets, like we were seeing before. Okay, so this is just one cluster, and in fact, in some other cluster, so in this case, the giant radio halo, as the name indicates, is really big. But in some other cluster, we have also some diffuse radio emission, but which is much more compact, so which we call mini halo. And these halos, they are generally surrounding the brightest cluster galaxy in the center of clusters. Okay, so I'm telling you all this, so it sounds really complicated. You know, we have a bunch of different emissions, and in fact it is, and in fact we don't really understand where this emission comes from. So far what we know from this emission is that there is cosmic electron and magnetic field in galaxy clusters. This is for sure, and this is what we see in this image. We have different possibilities for producing these cosmic electrons in the cluster. For example, as I was saying, AGN, directly injecting particles in the ICM. We can have also turbulent reacceleration, but for this we need also to have some pre-accelerated population of particles. We can have also this shock that we were seeing in this video just before, which can accelerate particles also. And finally, another possibility is to have cosmic protons, this time that will be accelerated along the cluster formation history and then interact with the thermal gas to produce pions mainly, which will eventually decay into gamma rays. So this is another possibility. In this case, you expect gamma ray, but you also expect these cosmic electrons, which maybe are related to what we see here. Okay, so far in the literature, which is dominant here in terms of flux. But the problem is that for this, you need to have a pre-accelerated population of electrons. So it's not so clear where they come from. Possibly they could come from these hadronic processes. This is a possibility. On the other hand, these cosmic protons, they should accumulate. Maybe there is some mic. So these cosmic protons, they should accumulate along the cluster formation history because they don't really lose energy, at least not quickly. So they should really accumulate along the cluster formation history. If you produce cosmic proton in the early universe, I don't know, at redshift, well, let's say redshift 1, for example, they will still be there at redshift 0 because they don't have time to lose their energy. So they really accumulate. Okay, so I'm saying of this, it sounds maybe a bit messy, and in fact it is, unfortunately for us, but the big question for us is, so where are these cosmic protons, in fact? And you see that all this is related to very rich and complex physics, so related to AGN, turbulence, shock, this hadronic interaction. You can also have revived plasma, magnetic amplification, and so on. And the big question for us is, in particular for gamma ray observation, is where are these cosmic protons? Because you see that if you have cosmic protons, then you expect interaction with the thermal gas, and for sure you expect gamma ray emission. So if you have cosmic proton, you have gamma ray emission, which produce, you have this unambiguous diagnosis for cosmic proton. And therefore, looking in the gamma ray band may help us a lot of in understanding all this. And so this is why we want to do this, in fact. Okay, so you may ask, okay, but maybe there are some prediction and some model for this cosmic proton cluster, and in fact, the answer is yes. So you have here a simulation showing a cluster that is producing this gamma ray emission from pion decay. If you have this pion decay producing gamma ray, you also have electrons that are produced at the same time, and you have also inverse Compton from this. But you see that inverse Compton is much less than pion decay. And this is generally what you expect in clusters. And for this reason, we mainly focus on this. So in terms of energetics, this is mostly what we expect. So I told you that the thermal energy of cluster should be more or less 80% of the total energy. This is what we can measure also from X-ray and so on. And for cosmic ray, we don't know very much, but models tell us that it should be around the percent level. So this is encoded in this parameter, which we will use in the following. which is basically the ratio between cosmic ray proton energy to thermal energy, more or less 1%. We expect also the cosmic ray spectral slope to be of the order of 2.2, so encoded in this parameter alpha. And the shape of the cosmic ray within the cluster, so this is not very well known, but we can encode it in a parameter that we call eta, which is expected to be more or less 1, and which will be, so scaled like this, we will have cosmic ray proton proportional to the thermal gas to some power eta. So for example, if eta is equal to 0, this means that the cosmic ray protons are completely flat within the cluster. They are the same density everywhere. If you have 1, you expect that they follow more or less the thermal gas. Okay, so I'm telling you about all these 3 parameters because this is what we will use in the following, so they are somehow important. But the problem is that, in fact, in the literature, there is a bunch of models which predict these parameters. So I told you a few typical values that we may use. But in fact, in practice, they are really not well known at all. So you can see, for example, here, so this is a fraction of energy that goes into cosmic rays as a function of the Mach number. Okay, it depends a bit on the temperature, but you can see different models from the literature. You can see there is a huge difference between the different models. The same for the profile, so the radial distribution of cosmic rays. You see, these are different models that are used, for example, in this paper. You can see we have like 4 orders of magnitude between these 2 different models, and the profiles are completely different. You see, so this tells us just that we have huge uncertainties that are, underlying this recipe. So in the image that was showing you before, for example, these predictions of simulated cluster, this means that we have really huge uncertainty, in fact, unfortunately for us. So what about observations? So in fact, even during the last 20 years or even more maybe, there were many attempts to detect this gamma ray emission. So either from individual clusters or stacking data, doing cross correlation also between different wavelengths. And so far, the constraint that was put on this parameter x is typically at the level of what we expect also from this model. So a few percent, let's say. So you can see an example of this parameter constraint here for a bunch of clusters by the Fermi collaboration in this case. So we are already starting, with this data to fit what we expect in terms of models. Okay, so in this, in the following, I will talk about this search for diffuse gamma ray emission, and mainly with 2 different ways. One of them with Fermi, basically. So I put this picture to illustrate the use of Fermi data. So Fermi, I guess you all know. So this is a gamma ray instrument that is a satellite, basically. So you have this gamma ray entering into the detector, which are converted, and you can detect like this this incident gamma ray. So like this, you look at relatively low energy. So we will see after in more detail. Another way to do it is from the ground, and basically you have your gamma ray entering into the atmosphere, producing secondary particles, which will eventually produce this Cherenkov radiation that you can image from the telescope that you have on the ground. And like this, you can reconstruct the direction and the energy of this incident gamma ray emission. So you have like flashes in the atmosphere of this Cherenkov radiation. So this is the way, for example, CTA is working. And we will talk about CTA later. And using these 2 different techniques, for instance, we can be sensitive from, let's say, tens of MeV to hundreds of TeV, more or less. Okay, so let's do that, and let's first focus on this first way to detect gamma ray, which is with Fermi, and in particular, looking at one specific target. Okay, let's try to be a bit more technical. So before we can really, extract information from the data, we need somehow to build a model and to know how to describe the data. And for this, we need somehow a relatively complex multi-wavelength modeling. So what we have done to do this is not to try to describe the microphysics, what is happening inside the intra-cluster medium, but to describe the different population of electrons, for example, cosmic ray proton, thermal gas, and so on in the cluster. And from this, we can derive some observables. So if we have some observables, then we can go back to these different quantities. But the problem is that everything is a bit interconnected. So for us, we are mostly interested in this cosmic ray proton population. But for this, as I told you before, as you have seen, we usually, what is relevant is to define the energetic of this population relative to the thermal energy. For this, we need to have somehow the thermal pressure entering into this model, which will give us the normalization. So we need also a model for the thermal pressure. The thermal pressure, so this is what gives us the SZ effect that I was mentioning before. You can observe that in the millimeter. So, okay, good. Simple, if you have millimeter data, measuring the SZ effect, up, you can come back to this thermal pressure and constrain this thing. Then you need also to model this interaction between the cosmic ray proton and the thermal gas density. So this is going here. You see, you have to model somehow cosmic ray proton, but also the thermal density of the gas. For this, we go here. And so fortunately for us, as I told you also in the introduction, the thermal density, this is what gives thermal Bremsstrahlung emission, which you can see in the X-ray. So if you have X-ray data again, you can come back like this and constrain this quantity. Okay, good. So now, okay, let's forget about this. So now we are here. If we have hadronic interaction, we can also, okay, we will produce gamma ray, which we want to observe and constrain, but then we will also produce these secondary cosmic ray electrons that are here. From this, if you have some magnetic field in the cluster, you will also produce radio emission, diffuse radio emission. So this is why, remember, the two were connected. I was mentioning radio emission also before. And then you can also have primary cosmic ray electrons that are not connected to this hadronic interaction. They will also produce synchrotron emission if you have some magnetic field that you have. Okay, everything is clear. So it's a bit, everything is a bit entangled like this, but basically what it means is that if you can model these different quantities, in the end, you can predict these different observables. And so from these different observables, you can constrain all this. This is really the goal. Okay, so just to show you how it looks in terms of spectrum. So, okay, let's focus on just on the gamma emission here in terms of profile. So this is how it looks. So this gamma emission is proportional more or less to the thermal gas and the cosmic ray proton because the two are interacting. And as a function of radius, it looks like this. So this is what I was saying more or less. If you have, I don't know, if you have, for example, cosmic ray protons that are proportional to the gas density, then you have this profile that is relatively compact and peaked. And if you have cosmic ray proton density that is constant, so this corresponds to this eta parameter, which was 0, I told you before, then still you have some relatively flat profile, but still a bit curved anyway. In terms of spectrum, this is how it looks. So you have this this shape typical for hadronic interaction, with a cutoff here that is related to no, in this case, no, yes, it's related to absorption along the line of sight. So from other processes that I will not enter into the detail here. But then the point here is that for different slope of the cosmic ray protons that you have in your cluster, you have different slope in the gamma ray spectrum, obviously. Okay, so in the end, what I mean here is that we expect a compact signal that peaks more or less, as you can see, at GeV energies. So for
sorry, what sets the normalization on the right? No?
The normalization, so yes, so I didn't really talk about this, but the normalization is given by this quantity. Okay, this tells you how much cosmic ray you have in your cluster, basically. So really, what we do here on this case, we model the cosmic ray population like this as a function of energy, power law in this case, and radius. So we have these two parameters, but then we also have this normalization. So for a fixed slope and a fixed eta parameter, if you change this value, you will just change the normalization. Okay, and then
in this case, for instance, you are using different normalizations for every curve.
No, in this case, this parameter is fixed. And so basically, this means that if you integrate over the curve, you have the same for more or less all of them. No, in this case, I'm showing the plot with this parameter fixed. And then basically the impact on the slope is mostly reflected in the spectrum of cosmic rays, of gamma rays. And this is mostly reflected in the profile of gamma rays also. Okay, so now that we have a model, we can start to look also in the data. So I've done it before. And in fact, there is a cluster that is particularly interesting, that is the Coma Cluster. So why is this interesting? Because the Coma Cluster is located here. So you can see as written here, so it's a massive cluster. It is nearby with a giant radio halo. So this means that we know that there is some cosmic ray acceleration already. And given this location here, there is minimal background. So in order to search for such a signal coming from clusters, this is an ideal target. So, and in fact, it was already, there were already some history behind this cluster because so the Fermi collaboration reported a 2 sigma excess in the direction of this cluster. At the time, it was, as I thought, too faint for detect investigation. Later, the 5 sigma detection claim was reported by this probe with tentative evidence for extended spatial structure. And 12 years of data after, the detection of a source was reported within the characteristic radius of the cluster by the Fermi collaboration also. So it was modeled as a point source at the time. So the question really is there gamma ray emission coming from the Coma cluster? So we try to continue this investigation. And in fact, this is what we have obtained. So we reproduce the result of previous work, basically using the Fermi data, producing modeling the background, subtracting the background, and this is the excess that we obtain with the data that we have. So you can see the characteristic 3 times the characteristic radius of Coma. So we have some diffuse signal well within this signal, and this is where the Fermi source is located. So the question is, it's really close to Coma itself. So the question is really, maybe this source detected in the Fermi catalog is really in fact the Coma cluster. Okay, so this is for sure. We confirm basically what was claimed before. And so for sure, there is detection in the direction of the Coma cluster. So now the question is, what is this emission associated with? So the first thing that we can do is to try to compare this data to other wavelengths. So for example, the Planck signal WT image that is tracing the thermal pressure. So you can see that the cluster is elongated a bit in that direction. So the same as what we see in the Fermi data. So maybe it's a hint of something here. In this case, this is a X-ray emission from Rosat, where you can see the gas density in comparison. We have also this secondary group that is located here, so the NGC 4839 group. We also compute the galaxy density from SDSS. So again, this elongation that you see here. And finally, the diffuse radio emission from WSRT, where we have in this cluster a giant radio halo here. And in this case, this is a radio relic. So it's tracing a shock in this case.
So Rémi, the contours that you are talking about coming from Fermi?
Oh yeah, sorry. So this white contour, this is basically this map here.
Yes. So what's the level of each?
So it's a TS map, and so if I remember, but maybe we can see here. Oh no, this is count. Okay, so I guess it would be because the peak was more or less almost 30 TS. So yeah, I guess this peak corresponds to 5 sigma more or less then. Okay, we can check later, but yeah, more or less it's this. Yeah, it should be so yeah. Okay, sorry, I don't remember exactly what I've done, but it's typical value, so it should be like I don't know, 5, 4, 3, 2 maybe. No, in terms of sigma. Okay, okay. I'm sorry, I'm not sure, but if you want, we can have a look later. Okay, so in terms of scale, also, okay, I don't know if we see very well or if it's more or less clear. So you see, this is just to look at scale, basically. So these are the 2 central galaxies of the Coma cluster, 2 massive galaxies, and you can see basically because of the Fermi resolution, and we have this problem in this case that we cannot really resolve, for example, the contribution from these 2 sources. So just to show you also this. So these contours again are from this Fermi analysis. Okay, so let's continue the investigation. So first, what we need to check is that the source is a steady source, because in gamma ray, as you know, a bunch of sources are variable. So if this source was variable, this would be a sign already that this is not attributed to the cluster itself. We checked that, and this is fine. This is a steady source. Then what we checked is to try to different models for the cluster to see if it was matching the data. Yes, so you can see the TS here. So for clusters, typical cluster model, we have a TS ranging so between 25 and 35. So it corresponds to a more higher than 5 sigma detection. Basically, the TS, the square root of the TS gives you sigma more detection. We also test a point source. In this case, it's a bit less, but the difference is not so significant. And in terms of profile, so this is what you have. So the profile as a function of radius. You can see in green a typical cluster-based model, and in yellow a typical point source model. And you see, so the green model match better the data, but you see, I mean, this is what is written here, that the difference, even in this plot, you can see, is not so significant. So at this stage, unfortunately, the nature of the source remains not so clear. It's possible that the source is associated with an AGN, for example. Okay.
This one profile for me is at a particular energy, or are you using integrated fluxes?
No, this was integrated flux. Yeah. So between I think 200 MeV and 300 GeV.
Okay, but you know that you will be dominated by what happens at the lower energies. Usually,
yeah,
right?
True.
You have more emission there, and then the DSF of the instrument will be very
exactly. So we try also to restrict to higher energies, but in this case, the statistics, we are really at the limit. So this is a problem. We need to compromise somehow, and yeah, given the test that we did, we cannot say for sure. Basically, this is the conclusion of this just Fermi analysis. Let's say is that that it's attributed to AGN, for example.
Yeah. And also, I guess we didn't try with different galactic diffuse emission models.
Yes, we did that also. Yes.
That's an important caveat, because you're only using a particular model for the galactic diffuse emission, while if you use some alternative model or many, you will see the systematic.
Exactly, and in fact, we tested this, and yes, this is clearly by far the dominant systematics.
Exactly.
Even if we
the bottom, there seems to be a transition at around 1 degree, right?
yeah.
So, yeah, is there some physical reason for this, or is it just an artifact?
I mean, you see the significance. So this is in unit of sigma, if you want. So it's within 2 sigma. So okay. Yeah, I mean, it's totally in agreement with those fluctuations. Okay, so at this stage, okay, this is a conclusion more or less, but anyway, we can say, okay, given all these problematics that we have from the radio data and so on, we can still say, okay, let's assume that this signal is attributed to the intra-cluster medium. We can even model a point source on top of this, and we can, explore what are the consequences of having this emission in this Coma cluster. What will be the implication for the cosmic wave physics? We can still do this, even if we are not sure that we have a detection. So this is what we do. And basically, we can constrain the spectrum, so it's the spectrum that we measure from Fermi, and fit this spectrum with a model in order to extract these parameters. So I remind you, this is the amount of cosmic ray energy divided by thermal energy. And so what we find, so you see the constraint that we have here, we find something around 1%, which is in fact what we expect more or less from this model that I was talking about. In terms of slope, however, you see this is the parameter alpha. You see the constraint. I mean, we have very large uncertainties, of course, but still we favor some very high slope. Well, very high. So some high slope, let's say, compared to what is usually assumed in this model. So if this is confirmed, this will be quite interesting. And for CTA, for example, we will see it can have strong implications. Okay, and so this first measurement of the cosmic ray proton content, assuming the hadronic origin. So even if there is a bunch of assumptions behind this, this is already pretty interesting in terms of cosmic ray physics in clusters. But still, we can go even a step beyond. And for example, okay, let's maybe go back a little bit. So now if we have, I'm coming back to this modeling. So now if we have measured this from gamma ray data, we can also predict what will be the associated secondary cosmic ray electrons that we expect and predict what we expect in terms of radio emission. And we can then compare also not only to gamma rays, but also to radio. So this is what we do up here. And so basically what we find is that the prediction that we have for the spectrum of the diffuse radio emission, if all this cosmic ray proton leads to secondary electrons, is here. So this is this blue band here. In contrast, this is what is measured in radio. So this means that the cosmic ray proton that we measure from Fermi cannot alone, at least, explain the diffuse radio emission in the Coma Cluster, because we are below. If we would have been above, this would have been a problem, because it would have meant that we expect more radio emission than what we measure. But in this case, this means that we need either we need to have some reacceleration process of these secondary electrons in order to rise this emission, or we need another contribution that comes from somewhere else in order to produce this emission. In terms of profile, this is the same. So this is the radio emission profile as a function of radius, and you see this is the same. Okay, expect in this case that the emission that we expect is a bit more compact than what is measured, in fact. So I don't know if it's visible really clearly by eye, but yeah, this profile, in fact, is really extended. Okay, and so in order to compare to what we can expect from state-of-the-art modeling, this is what we did. So we use a model of turbulent reacceleration. So that is in brown. And in this case, this model tells us that if you have a population of cosmic ray protons that leads to the secondary electron at this level, you expect to have turbulence that will rise your spectrum here. Exactly. Okay, so we have a very good argument, in fact, with this data with turbulent reacceleration models. This tells us also that we have more turbulent reacceleration in the outskirts of clusters than in the core. So this was shown in the profile. So basically, you need here you will boost your emission like this, but in the outskirts you need to boost it even more. So this means that you have more turbulent reacceleration in the outskirts. This is this plot, and this is also something that is expected, in fact, from this model.
So Rémi, in the red solid line is not really a fit. You are just assuming typical parameters.
Well, yeah, it's not a fit, but it's matched to the data. So this is from another paper. So I mean, so this is from Gianfranco Brunetti work.
But
so
question is actually if you're doing some kind of fitting or just using typical parameters and then the curve naturally goes this way.
No, the curve naturally goes this way, but I mean, so this plot, this curve is coming from another paper in which they really match. You know, they are not doing a fit, but they are really matching their model so that it's fitting the data. What is important is not really that this line is matching the data. What is really important here is that if you have this line matching the data for the total signal, this means that as an input cosmic ray electron population, you need to have this, which is a very good agreement with what we measure. So, I mean, then this is matched to Coma itself. So, of course, somehow it's matching.
Yeah.
So,
okay.
But yeah, what is really important is how you get from this to there. So this tells us that somehow the turbulence that you expect allow you really to boost your population of cosmic ray electrons to get the kind of signal that you expect. So yeah, somehow this is an interesting confirmation of the fact that this kind of turbulent reacceleration model, they can really allow you to explain the signal that you have in clusters. Okay, and so that's more or less the end of the story regarding this point. So I mean, this is more or less the conclusion that in fact if you don't have any source of reacceleration or any other source of electrons, these pure hadronic models, so in this case, they are not able to describe the data. You need to have something else. And this something else could be reacceleration, which provides a very, very good agreement with what we see. But also we have large error bars. So
in all this modeling that you're doing, you're assuming always that the full emission that you observe, in principle, is attributed to cosmic ray physics in the cluster.
In the radio emission, yes.
Yes.
Yes. But
in real life, probably you have maybe this 4FGL source is still there.
Yes, but okay, yeah. In this case, I mean, in the radio case, the point sources are removed, of course. So we only account for the diffuse emission. All the point sources, I mean, all the emission that's coming from individual sources, this is removed, of course. Yeah.
So you also have a model for the 4FGL source. You remove it from there? No?
You mean from Fermi in this case?
Yes.
Okay. In fact, we tested the different things. So here I'm putting a summary somehow, but we tested a model in which we have just the cluster that accounts also for this 4FGL source. Yes. But we tested also models in which we have cluster plus 4FGL sources, for example. Yeah. So I mean, then we have okay.
More constraining.
Exactly. So this is okay. Maybe I should have specified this here. The difference between these two constraints. This is what exactly this.
Okay.
Exactly. Yeah. But yeah, maybe one thing also is that even if we account, so yeah, even in the yellow case, when we assume that there is a point source plus a diffuse emission from the cluster, we have so it's less significant, of course, but still you see the constraints. Okay, it's reduced a little bit, but it's not changing completely the picture. So, okay, so let's move now to the second part, well, the third part in practice. And basically, this is a prospect work for the Cherenkov Telescope Array. Okay, so I mean, what I've just shown you before is a good illustration of the fact that with Fermi in particular, it's okay, you get really good constraint, but somehow it's difficult to know what you are measuring. So we see clearly some signal, but we are not able to clearly distinguish it, for example, from HGL. So this is one of the plans from the CTA. So we expect, so as you can see on this plot, we will be in a different energy range. So here, I mean, with an improvement that is very substantial compared to state-of-the-art Cherenkov Telescope Array, so like S. Compared to Fermi, you see the energy is different. And something very important for us is the fact that also we have very good angular resolution expected with CTA. So this is important for distinguishing, for example, diffuse emission from HGL. Okay, so maybe this is a bit outdated because it's always shifted. Okay, and anyway, I mean, so great angular resolution plus this wide energy range coverage is key for us. And also, I mean, maybe the main point here is that CTA can potentially detect diffuse emission in the cluster. And of course, this is one of the science states that we need to address. So just for you, if you don't, well, if you don't know, so CTA will be on two sites, one in La Palma and another one in Chile. So just to mention this. Okay, so in fact, yeah, the first flight of CTA has happened already. So you can see the picture here of the first one of the first telescope, and also some showers here coming from the Crab Nebula, in which you see the signal building up smoothly, and with the detection of the Crab Nebula. So this was already some time ago, but I mean, just to tell you that this is ongoing. So in fact, clusters are not missing that CTA will look at. So there are a bunch of other topics that will address the origin of cosmic rays and their role. So this is, of course, what I'm discussing is part of this, but also extreme environment, or also frontiers in physics. So for example, a lot about dark matter, galactic survey, also galactic center. Dark matter, of course, is one of the key topic. Some extragalactic survey, the surveys of the LMC, some transient, Pevatrons, and star-forming system, and AGM. Of course, AGM is a big part of it. Okay, but here we focus on clusters. And in the case of CTA, we have one cluster that is our main target, which is the Perseus cluster, for which we have 300 hours plane on source. And so we focus on a single cluster for a first detection. So from scaling arguments, I don't know what time it is, and maybe I need to speed up a bit. So from scaling arguments, we can argue that the Perseus cluster is really one of the best targets. For CTA, it's a good target in terms of angular size and relative to the field of view of CTA. And in this Perseus cluster, there is also a powerful radio halo. So it tells us again that there is some particular acceleration that are happening strongly there, and a bunch of ancillary data. So for all these reasons, this is a very good target. You can see an X-ray image of this cluster with this green contours that are showing the radio halo. Okay, so now in Perseus with CTA, we don't have data, but still we can take again this this picture and say, okay, let's assume some field, some thermal gas that we can measure, thermal gas density that we have also from X-ray, and then as given the radio data that we have, we can constrain models which will tell us what are the amount of cosmic ray photons that we expect, and if we have this, we can go there and predict the amount of gamma ray emission that we have. So we can use radio data together with other literature data that tell us what is the thermal gas pressure and thermal gas density to really predict what kind of gamma ray signal we expect. So this is what we do. Okay, maybe I will skip this because I don't have too much time, but this is not so much important. Maybe we can come back to it after. And so basically, this is what we do. So we can use some radio data, so the flux is a function of frequency. We have these 3 data points, and we have the surface brightness profile as a function of radius. So we can fit a model to this data, and this will tell us how much gamma ray signal we expect. So again, the spectrum as a function of energy, and the profile as a function of radius. So you see, we can predict what is the emission in terms of pure hadronic signal that we expect in blue, and also what we expect in terms of inverse Compton, that you can see, as I was mentioning before, this is subdominant. Okay, so once we have this prediction for CTA, we can use that, feed it into our simulations, and try to see what we can extract from this. So more or less, this is what we expect. So the problem in Perseus is that on top, I mean, as in most clusters, in fact, on top of the diffuse emission, so we have, of course, an instrumental background that we need to account for, but we have also 2 AGNs that are known to be gamma ray emitters in this case. So we need to account for them, and they are here. So we model them. You have this diffuse emission also that you don't see here, but if you, with this simulated data, if you do the analysis, you can remove the background, and this is the kind of background that you have. So this is integrated map over all the energies, but basically in terms of count as a function of energy, you have these 2 AGN in green here, the Perseus cluster in blue, and the background here that dominates in red. If you model all this and subtract the background, this is what you expect. So you see that you recover the signal coming from the cluster diffuse emission. You can see on top of that here the radio halo that we have in this cluster, and the comparison also with so Rosat in X-ray and Planck in SZ. So density and pressure of the thermal gas. Okay, so given this model, this is very nice. We expect some quite nice detection, in fact, of this cosmic ray emission in Perseus. Oops, yes. Okay, so now this is interesting, but the question is, okay, imagine that your model is not so good, and in fact you have much less cosmic rays than you expect. To which level can you exclude a given amount of cosmic rays? So we can also look at this, and basically we'll have a constraint on the normalization. So again, this X parameter that we can expect to put with CTA. But then this constraint will depend on the other parameter, which are the slope of the cosmic ray photons, and this eta parameter again, which tell us the shape of the cosmic ray photon profile. So you see this constraint in this color bands for different parameters. And we can see the comparison also to current state-of-the-art experiments, in particular MAGIC. And in the case of magic, the color, I mean, they are using some models that correspond more or less to this one. And so you can see that we expect to gain 1 order of magnitude, basically, compared to state-of-the-art constructs. In addition, you see that this is, in the case of this hadronic model, that we can scale to the data, to the radio data. And you see that the point will be there. So just at the limit, well, a bit below the magic limit, but for CTA, if this model is the reality, for sure we will detect it. But then, of course, we aim at more than just excluding model, but detecting the signal. So this is typically what it looks like in terms of spectrum that we can recover. So we are, in principle, really able to measure the slope, of the spectrum, which tells us. So if you plot again, so this is the same plot as for Coma with Fermi, you expect to measure something like this. And this plot is very important because it tells us where the cosmic photons are coming from. And in particular, it tells us, so if you go in that direction, basically you go to stronger shocks that accelerate particles and better acceleration efficiency. So reducing like this, going to lower value of alpha is going to stronger shocks, and going to higher value of x is better acceleration efficiency. So measuring this is very important for understanding cosmic ray physics in clusters. Okay, so we are able to measure the spectrum, but also the profile. So this is typical profile that we can measure, and again we can constrain. For example, here this eta parameter versus the normalization. And this time, so as you go down in this plot, like this, you have more cosmic ray proton transport. So which is, of course, what we expect, because if you have more transport, then you will flatten your profile. You will diffuse your cosmic ray population, so you will get a flat profile. So this is exactly the kind of thing that we can measure. And of course, again, it tells us a great deal about the origin of this cosmic ray population. Okay, well, maybe I can just quickly mention this. So I was talking about the main key science projects that we have for CTA, but there are also other kind of data that we may use to constrain this physics. And in particular, with CTA, we'll have an extragalactic survey, which you can see here. And of course, there are also a bunch of clusters in this extragalactic field. So we have already, in fact, last summer investigated what kind of constraints we could get from this. And in fact, also it's very preliminary. It is likely that this kind of data may be also very helpful in constraining the cluster physics. Another kind of sources that we can look at directly is this interaction between these jets produced by this central adjoining cluster and these cavities that are created by this interaction. So this is something that we may explore in the future, but again, this can be very interesting in order to understand how this AGN feedback is working in clusters. Okay, and that's it for this. I will just flash some summary. So, well, as you have seen, we have discussed clusters as cosmic laboratories, basically, with very rich astrophysics that we have mentioned. And in particular, there is, well, we expect some gamma ray emission from galaxy clusters. The presence of cosmic ray cluster implies gamma ray emission. And this cosmic ray proton population, this gamma ray emission gives us unique access on this cosmic ray proton population, and in particular, their physics in terms of transport and acceleration. So then I've been showing you two different kinds of axes, let's say. One of them is the gamma ray signal that we have towards the Coma Cluster with Fermi. So in which case there is clearly some gamma ray emission. And basically the conclusion is that we have excellent agreement with the diffuse emission model. But the point is that given the data, it's not possible to distinguish for sure the fact that this is not coming from an AGN. But even with this, we can still use this data to understand a lot the cosmic ray physics in the clusters. Regarding CTR, so CTR is under construction now. There are various science cases, including clusters, and in particular, so the Perseus key science project in which we are working, and well, in particular with Judith and Miguel, So I've been talking mostly about, well, uniquely even about the cosmic ray part, but of course there's also the dark matter part that I guess you know because you are leading it in CTA at the institute. So I will stop there. So thank you very much. And of course, if you have some questions, we can discuss.
Thank you so much, Rémi, for this comprehensive talk. Very nice, a lot of material. Other questions? Well, there were already questions, but are there more questions or comments for Rémi? I actually have more, of course. I can maybe ask one. I was wondering now about this XCR, the how efficient you are, no, to accelerate cosmic rays. So you said that the level you usually, I mean, the level that you expect is usually on the order of the percent, more or less, right?
Yes.
I was wondering about an absolute minimum for this one. I mean, can this guy go as low as you want? I guess at some point it's a problem, right?
Yes, exactly. So in particular, yes, the fact that you have well, the fact that you see radio emission somehow, I mean, it tells us somehow that you can accelerate cosmic rays, and in particular in relics. So, so yeah, for example, yeah, this kind of sources that you see in radio, this kind of like filamentary structures that are believed to be associated with shocks. So, if this is really some cosmic ray population that's coming from the shock acceleration, and if somehow we understand this shock more or less and model them in the radio, it implies, of course, some cosmic ray proton acceleration also. And this is already at the limit, you know. So there are some papers in the literature saying that maybe we don't really understand, in fact, this radio shocks, because otherwise it will imply this X parameter somehow to be higher than what is already constrained. So it's a mess, basically, and you know, there are tensions that are starting to, you know, on one side and on the other side. So it starts to be.
So in that sense, Rémi, with CTA, I mean, imagine that we go to Perseus. I mean, we are going there, of course. So we take we have the observation and we see nothing, right? And then you can constrain this parameter one more to even you know lower, right? This will be then a disaster for the theory part.
I think so.
Okay.
I think so. Yes.
So we're supposed to see some action.
I think so, but at the same time, you know, so I mean, you can see on this plot. It's so basically everything is from the radio cell. So you have many different kind of sources, and in the